if you only have one partially filled subshell, you can pretty much figure out your maximum multiplicity, and that you get your maximum multiplicity by thinking about the case where you spread out your electrons as much as possible within that subshell and having them with parallel spins, right? So for example, in lithium, 1s2, 2s1, maximum multiplicity is just 2, right? It's either spin up or spin down. Nitrogen, you have 1s2, 2s2, 2p3. You have 3 electrons to distribute in a p subshell. Maximum possible m sub s you can get is 1/2 plus 1/2 plus 1/2, which is 3/2, right? If your maximum m sub s is 3/2, then your maximum s is what? 2 times 3/2 plus 1, which is 4. So if you have 3 unpaired electrons, maximum multiplicity is 4. So you say that the term that you can get from the ground, the highest multiplicity term that you can get from the ground configuration of nitrogen is a quartet. Okay. Now, you've encountered Hund's rule for maximum multiplicity in freshman chemistry, right? And you were told that if there's more than one way, if anytime you have a partially filled subshell, because there's more than one way of distributing the electrons, the most stable one, the lowest energy arrangement of the electrons is one where you spread out the electrons, right, among the orbitals within that partially filled subshell and put them in parallel spins before you pair them up. Okay, that's why it's called the Hund's rule of maximum multiplicity, because that's what. Now, the m sub s that you get for that, the total m sub s, is associated with what? With the term that has the maximum multiplicity. In other words, what we're saying is, according to Hund's rule, okay, once you've derived the terms that are associated with a given configuration, the term that has the highest multiplicity is the one that has the lowest energy. So going back to carbon, what did we get? What did we find? We had a singlet D, a singlet S, and a triplet P, right? What is the ground term for carbon atom then? Singlet D, singlet S, triplet P. So from 1s2 to s2 to p2, you get 3 terms. This term right here, the triplet P, has the highest multiplicity, maximum multiplicity. That's the ground term. So of these 3 terms, those 9 functions associated with triplet P would be lowest in energy. Okay, so that's why it's called Hund's rule of maximum multiplicity. All right. So the Slater determinants associated with these, where you have unpaired electron, the most unpaired electrons possible. Okay. Those are the ones that contribute to the linear combination for terms with the highest multiplicity. All right. And you can sort of explain Hund's rule, okay, in terms of what is known as spin correlation. The idea is if you have electrons with a parallel spin, they tend to repel each other less than electrons with opposite spins. Okay. Although there's some recent research papers that indicate that that is not quite true, but we're not going to go into that. This is still what your book says. Okay. Now, for which of the carbon terms is, we already talked about this. Which of the carbon terms is lowest in energy? The triplet P, highest multiplicity. What about the helium, 1s1, 2s1? Did we do that earlier? Which one would have a lower in energy according to Hund's rule? Triplet S.